In this video, we will do some function analysis on this random crazy function shown here. We will discuss the domain and range, intervals of increasing and decreasing, points of discontinuity, and we will write a piecewise function for this graph. Let's start with the domain and range. Of course, you know that the domain is the x values. It's the set of x values of this function. So we need to basically list in some way all of the x values that are included in this graph, represented by this graph. So let's start with the first piece as we go from left to right. We have this little piece of a parabola here. This part goes from negative infinity to negative 2. Now, the question is, do I need to stop there? Do I need to say negative infinity to negative 2 and then do some kind of a union and break it up into pieces like this? The answer is no in this particular case because the next part of the graph picks up where the first part leaves off. And negative 2 itself is included in the domain. As you can see right here, this is a closed circle. So negative 2 is included. And then the next part of the graph just picks right up from there and keeps going. So there's no reason to break the domain here at negative 2. All right, any more than if I put a dot here and then I did something different, there'd be no need to put a break in the domain. It doesn't matter that there's a break in the, there's a vertical jump between these. That doesn't matter. Okay, so that's going to be the same deal when we get to the next break in the graph. Here at an x value of 3, this point, the x value of 3 is included, and then the next portion of the graph just picks right up from there. So there is no x value unrepresented. Every x value is covered from negative infinity to positive infinity. Every single x value is represented on this graph somewhere. So that's why the domain will simply be negative infinity to positive infinity. Do not split up the domain into pieces. That is not necessary. Now, the range. For the range, we should be basically thinking like this. You understand that the range goes from bottom to top. Oh man, that's not a good color. Let me change it to green. All right, the range is the y values of the function. So for the range, we need to talk about how far the graph goes from bottom to top. Again, you're not going to need 3 separate pieces to the range. This is one function. This is not 3 separate functions. This is the graph of a single function. So just overall, looking at this function as a whole, what is the lowest point on the graph? The lowest point happens right here, okay, because of this little dot right here. And this is, of course, at negative 6. So we will begin our range at negative 6. I'm going to go ahead and put a square bracket on the negative 6 because negative 6, this point is a closed circle, so that means it is to be included in the range. Now, obviously, from there, the graph goes up forever. The only question is, are there any gaps? All right. So as I move this green line up, is there any time that I'm not touching the function? All right, because that would represent a y value that was not included in the range. So far, I'm still touching. All right, it doesn't matter that I'm hitting the graph twice. Okay, that doesn't matter. Negative 2 is part of the range. Negative 1 is part of the range. Still touching. All right. So notice as I go through this area and I'm hitting I'm touching multiple portions of this function. At no time is there a place where this green line is not touching the function. That means that every y value is covered. So this function touches every y value from -6 on up, and then it just goes up from there forever. So that's why the range will simply be from -6 to infinity. All right, there's no break in the graph as I move from bottom to top. There's no time that I wasn't touching, so there's no break in the y values. Okay, so that's it. A common mistake is students will give me a range for this piece of the graph, they'll give me another range for the middle piece, they'll give me a third range for this piece. That is incorrect. You have to treat the function, this whole graph is one function. You have to treat it as a whole. Now, let's talk about intervals of increasing versus intervals of decreasing. One thing I need to emphasize to you is that as soon as we start talking about intervals of increasing or decreasing, please understand that we are talking about x values. Okay, hold on, I keep losing my pen. So these intervals of increasing and decreasing, these are x values. All right, we are only talking about x values. All right, now, if I were to travel along this graph from left to right, you know, like I was going to travel it like it was some sort of terrain. For a certain part of the journey, I'd be going downhill. So you can see I'm going downhill, downhill, downhill until I get to here. And then I'd be going uphill, all right, from here to here, I'm going uphill. Now I have to jump down to here, but I'm still going uphill. But then to continue, I then have to go downhill for a while. All right, and then there's a jump right here, and but then after the break, I find myself going uphill, and I'm going uphill for the rest of the way. So downhill, uphill, uphill, downhill, uphill. Everywhere that I just colored in red is going to give me a decreasing interval. Everywhere I just colored in green is going to give me an increasing interval. Okay, now, except for one thing that you have to be very careful about, and that is we're only talking about x values. So let's do the increasing intervals first. So because I'm only talking about x values, can you see that this increasing interval, all right, this little guy right here, is going from -3, I might have to use a different color. Okay, what color would show up right now? All right, maybe I'll just erase this for a second. All right, so I'm doing this little piece right here, but I'm trying to do only the x values. So the x values are right here for this piece of the graph. This is from -3 to -2. Okay, so that is an increasing interval. All right, so it's increasing from -3 to -2. All right, now I'm going to put another interval for this portion because of the jump. Because I went from high to low, technically it's not increasing continuously from here to here, from -3 to 0, because I went from high to a low, and that was a decreasing for a moment there. So I'm going to pick up with another piece of the interval down here. So I'm now gonna talk about this portion of the graph. Okay, this portion. The x values though go from -2 to 0. All right, so looking at the x values, -2 to 0 for that part of the graph. So -2 to 0. Okay. When you're doing increasing and decreasing intervals, always use parentheses, not square brackets. It doesn't matter if the endpoint is open or closed. The endpoints are not included as they don't count as increasing or decreasing. Okay, so my next increasing interval is going to be this green portion of the graph over here. Now I'm just going to erase this to make it more clear, but just remember this is the portion of the graph we're talking about, but I'm dealing with the x values only. All right, so on the x values, it starts here, and then this graph goes to the right forever. All right, it starts at an x value of 3, but then, sure, it goes up, but all I care about is the x values. I care about the fact that this is going to the right forever. So 3 to infinity. Those are the x values represented by this portion of the graph. So I'm going to say union 3 to infinity. Okay, those are the increasing intervals. All right, now let's talk about the decreasing intervals. Okay, so the decreasing intervals are these that I indicated in red. Again, don't forget, we are only talking about the x values. So this portion that I highlighted in red, it goes from here to here. But I have to read it from left to right. So from left to right, this goes from -infinity to -3. So that is a decreasing interval is from -infinity to -3. Union. Okay, so that is that portion. I can erase that now. Now, how about this last portion? It is decreasing from here to here. All right, those are the x values for this portion of the graph. If I focus on the x-axis, it goes from 0 to 3. So that is another decreasing interval going from 0 to 3. Okay, so that is how you do increasing and decreasing intervals. Now, when we talk about points of discontinuity, we're talking about jumps in the graph, like this one. Okay, we've learned about 3 different types of discontinuity. Now, one of them is called a jump, and that's what's happening right in here. Right in here, this kind of a break where it jumps from 1 to -4, this is called a jump discontinuity. And we're going to mention the x value where it occurs. So we would say there's a jump discontinuity at -2. Okay, so we're going to say jump discontinuity at x equals -2. Okay, so that's what a jump discontinuity looks like. A removable discontinuity would be just a hole. So like say if I had something just like this would be a removable discontinuity. It would just simply be a hole. An infinite discontinuity is an asymptote. So if I had an asymptote, and so say if I had one part of the graph on one side of the asymptote, and then I had another part of the graph on the other side of the asymptote. Okay, the asymptote would be an infinite discontinuity. So let's see what's going on at the other break in the graph. Well, here's the only other break in the graph is right over here. But this is another jump discontinuity. Okay, so this one occurs at x equals 3. So we will say, well, I already said jump discontinuity at x equals -2. So I guess I could just say and x equals 3. Just keep it simple. All right. All right, so that's it for the discontinuities. Now it's time to write the piecewise defined function that would graph the function shown. All right, so we're going to write a function for each piece of this graph. So starting with this piece right here, all right, that goes like this. All right. Notice that the parent function here is x squared. Hopefully at a glance you can see that this is a portion of a parabola. All right. Now, that's the parent function. X squared itself would be over here somewhere at the origin. All right. Now, you can see that instead of being at the origin, this parabola or piece of a parabola has been shifted over 3 units to the left. So now the vertex is here at -3, 0, but it's been shifted 3 units to the left. So because of that, all right, that tells me that instead of simply x squared, what I have is x plus 3 squared. All right, this would be a transformation of 3 units to the left. So that's why this is x plus 3 squared instead of just x squared. Okay, so now that I've identified that portion of the function, I can just go ahead and write that down. This is going to be x plus 3 squared. But next, I need to mention the domain of this part of the graph. So look at the x values. So this part of the graph, if I stare at the x-axis, maybe I'll just use a highlighter. This goes from -2, and it goes to the left forever. If I say it from left to right as I should, it's -infinity to -2. So that's the domain for this part of the graph, so we need to include that. So we'll say -infinity to -2. Let's see, will this be an open circle or a closed circle? This is a closed circle, so I'm going to go ahead and put a square bracket on that. So this is what we called interval notation. There's another option that we have. You could use inequalities for the domain. So you're going to choose one or the other. So I usually use interval notation, but sometimes instead of -infinity to -2, you'll see this. X is less than or equal to -2. That's another way of saying this domain part. All right? Can you see that's the same thing? Less than or equal to -2 covers the same x values. So either way, you choose. All right, now let's move on to this graph down here. I'm going to change colors. So let's look at this portion of the graph right here. The parent function seems to be an absolute value function. So the parent function of this would be like absolute value of x. Now this graph is not the graph of the absolute value of x for 2 reasons. There are 2 transformations that are happening. One is that it's upside down. A normal absolute value of x function would be a v, but it's a v that is going upward like this. All right, this is what absolute value of x looks like. Okay, this one is facing down. So that tells me that there's a reflection over the x-axis. So that tells me that there will be a negative sign in front. But there's something else that is different. The slope should be 1. If you look at the right side of this v, see how I carefully drew it going up 1 over 1, up 1 over 1. So this slope should be 1. But when you look at this graph right here, it's not going down 1 over 1, down 1 over 1. This is going down 2 over 1. Okay, so this has a slope of -2, not -1. So that's why, in addition to having a negative sign, I'm going to need a 2 in there. So it's really -2 absolute value of x. Okay, because of the slope. All right, so that's it. This is the function of which this is a piece. Now let me erase my extra lines. Okay, so now we've identified that this piece of the function is a piece of -2 absolute value of x. So let's go ahead and include that in our piecewise function now. So we have -2 absolute value of x. All right, now it's time for the domain. The x values here go from -2 to 3. From -2 to 3. Notice the open circle and the closed circle. So it's like -2 to 3. So I'm going to need parentheses and a bracket. Okay, awesome. So maybe I'll just switch this up. So, or I could have said -2 is less than x, which is less than or equal to 3. If I wanted to use inequalities, this is the inequality way of saying this same thing. Okay, it's x goes from, the interval notation says that we're dealing with x values between -2 and 3. This is another way of saying x is between -2 and 3. The parentheses are indicated by the less than sign with no equal to, showing that the -2 is not included. The little equal to, less than or equal to, is how we show that the 3 is included, same as the square bracket. All right, now let's get back and do the last part of this. Okay, so this portion of the graph, I think I'll just switch back to blue. All right, now we're going to do this portion of the graph. All right, now the parent function of this portion of the graph is going to be x cubed. We have memorized that x cubed does like this type of thing. All right, it makes this type of a wave. Okay, let me just get rid of that. And we see that the wave is happening right here. Now, x cubed itself, as you saw that I just drew, it normally goes through the origin, like this. All right, that's where the inflection point is, where it switches from being downward to upward. But this graph, the inflection point is here. So that shows me that the x cubed has moved to the right 4 units. All right, just hold that in your brain. So that's why I'm going to modify this slightly to show that it's moving to the right 4 units. So that will be x minus 4 cubed. All right, parent function x cubed, but move to the right 4 units. Okay, so x minus 4 cubed. Okay, now it's time for the domain. This goes from 3 to infinity. It goes to the right forever. So from 3 to infinity. Notice the open circle here at an x value of 3. So that's why I'm going to put parentheses, not a square bracket. 3 to infinity. Why did I put of? That's supposed to be or. Silly man, or. Okay, so, or, from 3 to infinity, as an inequality, that would be x is greater than 3. Okay, and I'm noticing that my infinity looks a little bit like a negative infinity. That's going to bug me. Okay, so that is how you do it.